I'm going to share with you the agenda before we begin our presentations. You can see here we have two speakers, or perhaps more, depending upon how they decide to make their presentation, focused on today's collaboration. And with this, I will like to invite and introduce also Dr. and Professor Masahiro Kurata from Kyoto University, who will be giving us a presentation on the Tokyo Metropolitan Resilience Project, test number 3, the one you'll be witnessing today.
I'm sorry to tell you, and please mute yourself, and I can hear some noise. Thank you.
The host can mute anybody. Please go ahead and mute them if they're not muting themselves.
Yes, I'm looking for them. Yep.
Uriel, can I start?
Yes, please, Dr. Kurata. I think everybody else is muted now, except yourself. Oh, no.
Julio, it's Adriana.
Yeah, I keep looking for her.
Hi, everyone. I'm Masahiro Kurata from Kyoto University. I'm speaking from the catwalk of EDefense side. I was fortunate to be here, and I'm very thankful to the organizer of the meeting and giving a chance for us to have our presentation today. So I'm going to have our presentation on the holistic assessment of seismic damage in medical facility, test number 3 for steel and prevention structures. And Dr. Yosuke Kawamata is the co-PI of the project. We actually had a large group of committees for preparing this test. We spent past 4 years to prepare the specimens with steel, non-structural components, and the medical components, and the monitoring equipment inside. This is our structure. Left side is the fixed base, typical low-story, low-rise steel structures, 1 by 2 bay, and the grids is around 5 to 7. In the right side, we have base isolated structure. Here we use a low friction, single friction pendulum system, and 2 structures were connected by corridors and expansion joints. The objective of the project is the holistic vulnerability assessment of medical facilities, including non-structural components and equipment, and also the quantitative evaluation of functionality loss and the recovery after extreme earthquake. We also implemented advanced technology to identify functionality and promote a framework to avoid unnecessary disorder and support safety by hospital management. I got a cheer so the children's so also the specimens, the left side one, the 4-story fixed frame was designed for the critical structure, following the code building law of Japan with reserve strength of 50%, so 1 point times larger strength to the code minimum level. And we chose the beam. We aimed at beam collapse mechanism with column-based yielding prior to column. This is a typical design in Japan. Column-based yielding is not very typical in the rest of the world, but we have this kind of choice for the economical design. And the base isolate structure was designed also for critical structure. And the single friction pendulum with elongated the natural period of structure to around 4.5 seconds. And we had a lot of non-structural components. They are anchored for designed for 1.5G to 2.0G gravity. This is the plan view from the top. The left side is again a fixed base 1x2 bay, and the right side is base isolated 1x1 bay. This is the elevations. The left side structure has around 15 meter in height, and the right side has around 10 meter in height. And we connected two buildings with corridors and expansion joints. An expansion joint was actually pretty expensive, so we only had the inner side, and then we gave up the exterior side. And also one side was equipped, but the other side of the corridor was no expansion that we had. We installed many non-structural components, and on the roof we had elevated water tank. Two of them are fixed to the roof, the concrete slab. And one was designed following the older regulations. The other was designed and anchored following the latest regulations after the Tohoku earthquake. And these tanks were also connected with the piping system. This piping system just sit on the frame type spacer, so they slide during the earthquake. And then typically those sliding of the piping damage the connection part to the tanks. In our test, we use the flexible the connector, so we don't expect the damage, but we try to measure the demand to the connections. And in the other floors, we had ceiling systems, and then also piping system above the ceiling, and there also air conditioners, and the lighting was installed. We collected a lot of medical equipment using these 3 areas. I visited many hospitals and then asked to give us the medical equipment which are no longer to be used. Lots of them. And then this is the layout of the floors. In the 4th floor of the fixed space, we had a patient room, and we also included ECMO, which is for the COVID-19 the patients. And the left side is a NICU. We had 2 layouts, but 2 exactly same layout, but different the floor sheeting. These 2 floor sheeting has different the friction coefficient, and also the flexibility for the vertical, like the weight. And the 3rd floor, we had a surgical room in the left side, and a dialysis room, and then their machinery in the right side. In the base side floor, we had the dialysis room as well. On the 2nd floor, the left side, we had a staff station, laboratory, pharmaceutical, and in the right side, consultation and treatment room. And for base isolation, we had a NICU. And first floor base isolation building was dedicated for the laboratory, pharmaceutical, and then pharmaceutical. So this is a layout. So we had a lot of medical equipment installed, and thanks to the close collaboration with Kyoto University hospitals, the physicians and the nurses, and also the clinical engineer helped us to realize the layout with very close to the real conditions of the operations in the hospitals. At the same time, we hosted blind prediction competitions for this integrated complex structure systems. We had our phase 1 and phase 2 blind prediction contests. The phase 1 is mainly dedicated for structural and non-structural. Then phase 2 is non-structural and then functional. The competitions of the phase 1 closed, but the phase 2 is still ongoing. And these are some typical items included in the phase 1 competitions. floor acceleration, story drift, BMN rotation, column-based rotations, and etc. For the non-structural part, we asked the competitors to predict the responses of the piping, elevated tank, and then also the some typical important medical and also the functionality of equipment one of the tasks to the partition the competitors. Thanks to the advertisement, also by we asked Julio to distribute our flyer through the design safe, and we had 82 entries from 21 countries, pretty diverse, geographically diverse in the world. Among the 82 entries, before the deadline, 17 teams submitted their predictions. Let me show you the construction sequences of buildings. We just finished our test last week, so I cannot share you a lot of the test data, but let me introduce how we built the buildings. This is the view from June, and then this is the beginning of the construction in July, and foundations set up, and then column bases set up for exposed type column bases. We started the instrumentation for the gauges, and then the foundation construction started at the same time in August. It was very, very summer with 40 Celsius. And just in 2 days, the erection was completed in the mid of September. And we sheeted the floor, deck slab, steel metal deck slab, and then this is the view. And we also fixed the column bases with mortar. We connected the columns and started install non-structural components and equipment. Like this is the metal system for the partition walls, typical in Japan. And for the elevated water tank, we are not allowed to use the water at EDefense. We decided to fill the water tank the sand. It was really tough process and a nice exercise there. And at the same time, we started preparing the cabling and the sensors for the test in October. We had around 1,000 cables with 20 meters to be prepared. This is the view, a nice clear sky with the specimens. It was around the end of October. We completed the work outside the EDefense here, and then ready to transport them into the test building. At the same time, the US-Japan specimens, which Larry will present after my presentations, their specimen arrived around October 24th, and then we started preparations for the US-Japan test as well. So 2 tests preparation was ongoing parallelly. This is the construction of the one part of the specimen for US-Japan. Okay, this is a photo of the Tokyo Metropolitan specimen, base-sided structures transported by crane, and the 2 specimens was set inside of the EDefense test buildings. We had a lot of scaffolding to install carrying in the medical equipment. Same time instrumentations. And finally, we carried in all the medical equipment in mid-November and laid out them inside the building. We had like real baby mannequins. We had 8 of them actually, all rent from the many hospitals around Japan. and we really try to make the conditions similar to the real hospital buildings. This is a view of surgical room. Okay, so we did a loading in December 1st and 4th and next week. So just completed last week. And the ground motion we used was JMA Kobe, which is intended for the near fault earthquake. And we also used the long duration earthquake expected, which is assumed for the Nankai Trough in west side of Japan. These ground motions are pretty demanding to the non-structural components and equipment. In the test, we only used the 50% scaled ground motions because they are super powerful. This is let me show you the videos. I hope it will work well. Okay, these videos is uploaded in a new YouTube site, so you can check later. Our test was broadcasted by the TV's news. So let us see. This is the nice view of the EDefense. So we had our press conferences on the day 2, where we installed the long period, long duration ground motions. This is how the medical equipment responded for long period, long duration earthquake. And this is the view inside of the fixed base buildings, surgical room. According to the medical doctors, it's probably not possible to continue the medical operations after such earthquake. While both buildings are actually quite healthy, and we did the rapid screening of the structure by the registered volunteer structural engineer and the medical disaster medical assistant team together. This was the first time here with the first time trial where medical communities and the structural engineering community work together for such. He's the head of the emergency ER in the Kyoto University Hospital. He's the partner in our project. So left side, the base side of the building was the protection system worked pretty well. So we didn't see even the 1 inch of maybe this observed like 2 inch of the displacement, but not more. This is the view of the press conference. So as I explained, we did some trial for rapid screening damage observations of hospitals with the collaboration of the physicians. This is one very big the challenge at the disaster side, where these physicians go to the affected area maybe sometimes earlier than the structural engineer, and they need to rescue the patient from the hospital. So we wanted to make some new idea on how to assist those the physicians right after the earthquake. Fortunately, we had the good exposure to meteors, and our test was reported on 7 TVs and then 3 newspapers. A brief test summary. I cannot show you the details because the phase 2 completion is still ongoing. On the day 1, the structure was mostly elastic at the first and second ground motions. And then later at the JMAC over 50%, some yielding of column base was observed, and also the beam. Day 2, we had a severe yielding at the column bases and the beam count connections. Day 3, we had a failure of the column bases and then test completed. This is acknowledgement in the funding support for various agencies and the collaborators and suppliers. And the collaboration with the medical society was also really much appreciated here. Thank you for your kind attention.
Thank you, Masahiro, for a very interesting presentation. I'd like to, in the interest of time, invite Larry to give us his presentation. Larry, I'm going to try while you get set to see if Mr. Tola can turn his volume off. Can you mute yourself? ¿Se puede apagar el volumen, señor Tola? ¿Está escuchando? Okay. I don't have host control, so Larry, I've sent emails and everything. Hopefully you can go on with your presentation.
Okay, thank you, Julio. Are you seeing my presentation mode screen?
Yes, Larry.
Okay,
yes.
Thank you very much.
Seeing speaker view, Larry. We're seeing speaker view.
Okay,
yeah.
I will. Okay, so now you see the presentation.
It's distorted.
It's not fully on the screen. It is in presentation mode.
Yeah.
Okay, let me try one. Is that better?
Yes.
Okay.
Yes.
Very good. All right. Welcome, everyone. Thank you for joining the meeting. It's a great honor to be here today and to present on the work that our team has been doing on this relatively new project. The title of the project you see here is Frame Spine System with Force Limiting Connections for Low Damage Seismic Resilient Buildings. And as you can see here, we have a very large team. It's been an extensive collaborative effort between those of us in the US, Illinois, Lehigh University, Oregon State University, and then our colleagues in Japan, Kyoto University, EDefense, Hokkaido University, Waseda University. And so I just want to start by saying a very big thank you, domo arigato, to our Japanese colleagues who have been phenomenal on this project. As you can imagine, the challenges of conducting an international research effort on the other side of the world in the middle of a pandemic is quite extensive. And so it's a real credit to them that we are at this point and that we are doing the tests that we're doing this week. So thank you very much to everyone who's contributed. We really sincerely appreciate it and want to acknowledge all of you very extensively. In addition to the primary collaborators that I listed there on the first slide, we have an extensive team of supporters that we need to acknowledge. Of course, this project is supported on the US side by the National Science Foundation, with Joy Palski as the program director. We've done testing in the US at the Lehigh NIERI site. And we have, of course, been collaborating extensively with Masahiro Kurata through the Tokyo Metropolitan project. We've received support from AISC, steel donation on the US side, and then extensive donations of materials through Nippon Steel. And also, as Masahiro mentioned, all the medical equipment that was a part of their structure. We have also been able to use most of that in our tests, and so you'll see that coming up in a few minutes. So again, thank you to all the collaborators and supporters of this project. I just want to acknowledge the significance of this meeting, in particular going back a few years to the first NHERI NIED EDefense Joint Research Collaboration meeting in 2017 was where the concept for this project first was born. I attended that meeting along with Barb Simpson, and we had some conversations with Yusuke Kawamata and Matsuhiro Kurata. We learned about the Tokyo Metropolitan Resilience Project, and in particular, their portion of it on steel structures and protective systems. And that was really what got this idea started about pursuing this international research project. Before we had funding from the National Science Foundation, we received a seed grant from a DPRI at Kyoto University, and this was instrumental in us having the opportunity to interact even before we had a project and really do some extensive collaboration and planning across between the US and Japan. And that led to the proposal being funded in 2019, which gave us the NSF funding that has supported the primary work that we're talking about today. Here's a few little snapshots into the collaboration meetings that we have had over the last couple of years. And we've had some really great discussions, some real extensive collaboration in developing ideas and planning for these tests. And I might add that we've just enjoyed spending time together as well. It's great to collaborate in research, but it's even better to make friends from around the world. This is the basic concept that we'll be talking about today in our project. And this is just a little figure from our proposal, and this is roughly where we were last August. We had the concept of developing a novel and economical steel frame and spine lateral force resisting system with force limiting connections to control multimodal seismic response, not just to protect the building structure, but also to control drifts and accelerations, to protect non-structural components and building contents. So skip ahead 16 months to where we are today. And here we are conducting full-scale building tests on the EDefense shake table. And that may seem 16 months sounds maybe like a long time, but when you're developing such a test as this, it has seemed incredibly short. And there have been many long days and nights all around getting us to where we are today. So again, great thanks to all who have been a part of this effort and brought us to this point. I'd like to turn it over to Richard Sauce to talk a bit more about the system concept. And so Richard, I'll give you the floor now.
Okay, thank you, Larry. The starting point is just looking at how a frame or a moment resisting frame behaves. And in concept, we can see the deformation that's possible in that frame under lateral force. And we know in design, we have mechanisms to kind of distribute the nonlinear demands or the inelastic demands within the structure. But research done over the last 10 or 15 years by many people shows that it's really likely that despite those measures taken in design, that we will end up with some concentrated deformation demands in one story somewhere in the structure. And often it's the first story. So go to the next slide, please, Larry. So the concept that we're utilizing here is to include an elastic spine within the system to help distribute that deformation over the height of the structure. And spine-like systems have been studied for probably 25, 30 years, kinds that have controlled moment at the base or even no moment, like a pin at the base, like you see in this schematic here. So they've been around for some time. And if you go to the next one, they're very good at distributing the deformation demands over the height of the structure, preventing those kind of story mechanisms from forming. But past research has shown that the higher modes tend to create high levels of accelerations and inertial forces within those systems, as opposed to the original bare frame by itself. So if you go back, Larry, what we see is that the spine is really effective at controlling story drifts and creating a more uniform deformation profile over the height of the structure. but the downside is the potential for large accelerations and forces, inertial forces, compared to the frame by itself. So what Larry mentioned before is we explored the idea in the proposal and also over the last 16 months of how to include force limiting connections between that spine and the MRF. In a past project that I worked on several years ago with Robert Fleischman and Jose Restrepo and Giorgio Sampras, we looked at this concept there, but we didn't have the spine MRF system that we see here. It was a different system, but we learned that we could really control the accelerations and the forces. So please go forward, Larry. So in this project, we looked at different ways in which we could connect the spine into the MRF building. And one method we came upon right away as part of even within our proposal was to use some U-dampers, which are made by Nippon Steel Engineering. They use them often in like a base isolation system or other types of systems, but we thought we could use them individually as the force limiting connection between the MRF and the spine. And for some places in that structure, that worked really well. And we have them in the structure, as you can see here on the third elevated level in the building. For other places in the structure where we had greater force demands or larger stiffness requirements, we had to develop an FLC, or force limiting connection, ourselves. And that came, I think, as a result of trying hard to make the U-damper work for this project. And we just couldn't find the architectural space to fit enough of those U-dampers in there to make it work. So we developed this this tongue-shaped FLC. And this is a test that was done at Lehigh. We developed this, designed it, tested it within about a month or so, because the schedule Larry mentioned before. And so it's actually performed quite well in our tests in the lab. And the picture that you see there, as well as the force deformation behavior you see on the right-hand side, is a little misleading because it shows a test going out to 75 millimeters of deformation. And we have no intention of actually going there in these tests. We really work within about 20 to 25 millimeters of deformation and try to keep the relative motion between the MRF and the spine controlled in that way by stiffness and force control. And later on, you'll see some data from numerical simulations that shows our ability to control accelerations by including this device. I'm going to turn over to Jim Rickles. Jim, going to talk about one of the simulations that we did at Lehigh.
Yeah, thank you, Richard. So hopefully everyone can hear me. The next step of the project, what was done at Lehigh, was to investigate how do these FLCs perform under earthquake-type conditions, not only with respect to the level of the ground motion, but also the interaction with respect to the spine and the moment-resisting frame. So what you see here on the left-hand side is a schematic of the structural system. The center member actually is the spine. It's pinned at the base and it's connected at the first and the third floor with the FLCs. And I think at the other locations, there's rigid type connections. The remaining two vertical members, the far left and the far, or the part of the MRF columns. And of course you can see the beams. So the hybrid simulation involved modeling physically the FLC. You can see the one blue colored element. That's actually part of the physical experiment, which is on the far right. And the remaining part of the system is modeled numerically. The ground motion that was used here was one that Jessica, our PhD student, had investigated with Barbara Simpson at Oregon State to decide what ground motion would be represented.
Jim, you're muted now.
Sorry, I don't know how that happened. I don't know where I should continue, but the ground motion here was scaled to design basis earthquake. That's a roughly 500 year return period. I'm getting some strange things on the screen here, sorry. So in any event, what we'll see here is the actual hybrid simulation. The middle schematic here will show the force versus deformation, the FLC. The lower below the structure will be the ground acceleration. The right-hand side is the displacement time history. The photograph you see here, we typically have video. This particular time we don't, but I want to add the note that we use conventional instrumentation, including old school whitewash, but also we used the DIC, which is digital image correlation. one of the goals out of this test was to go ahead and utilize also the data that Oregon State can use that to calibrate some of the numerical models for subsequent numerical summation. So Larry, I think if you could hit the button, it will play the hybrid simulation. So a few things you'll notice here is, as Richard was alluding to, in the quasi-static test, we took that out quite a bit, the specimen that's cyclically symmetric. Here it's not cyclically symmetric, and in addition to that, the maximum deformation here is about, 15 millimeters here. There is some small residual drift, but in any event, these tests are going to be continuing looking at other systems, but the purpose here is to validate the FLC, how it would perform with the theme structure that's tested at EDefense. And subsequently, Barbara Simpson, Oregon State, and her students use the results from this test to calibrate the models and continue to do numerical simulations. Okay, thank you, Larry.
All right, thanks, Jim.
Yeah, so I think I'm up now. Hello, everyone. So as Jim said, we use the information from the Lehigh test in order to calibrate our models and build a model of the FLCs in OpenSeas. We also had quite a bit of epistemic uncertainty related to that model. And so I just want to give a huge shout out to the two students that worked on the modeling for this project, David Rivera, who actually graduated with his master's, and then Brian, who's on this call, who's been, I would say, spending many a late night leading up to this test. They've been really incredible throughout this process. But what you'll see on the left is because of the uncertainty, we ran a number of different models. And then we also had to select only a few ground motions to actually choose for our experimental testing. And so on the left, you can see this is from Brian's model. He's just scaling the ground motion up. And what he's looking at is the bare frame, moment resisting frame without the spine. That's going to be the gray line here. And as you can see with these gray bars, as you scale the ground motion up from 0 to 100%, those gray bars really tend to increase. And that's because that MRF is forming a story mechanism and getting concentrations of drift in that first story level. In contrast, if you look at when we add the spine, and the spine is actually there in both these red and green lines. The green lines represent the spine connected to the MRF with the FLCs. And the red line represents the spine connected to the MRF with a rigid type connection without the force limiting connections. And you can see that the presence of the spine really does decrease those drift demands. So even though there's a tendency in the base MRF to form a story mechanism, when you add this spine, you can impose a more uniform drift distribution, and you can reduce the drift demands in a single story. So that's the figure on the left. Now, Richard mentioned this idea of having higher floor level acceleration. So if you look at the figure on the right, as your ground motion level increases, as you can see, the MRF is able to form a story mechanism, so it really can't pick up those higher mode acceleration demands. But when you add the spine, you can really increase the accelerations quite dramatically. Now you have a stiff vertical element in your system. And so if you compare those red bars to the green bars, the red bars are without the FLCs. So that's when the spine is rigidly connected to the MRF. And then when you add the FLC in, you have now a mechanism of limiting those higher mode acceleration demands. And so you can see that green line sort of plateaus as you get up to higher demands. So the joint combination of FLC plus spine can reduce drift demands and decrease acceleration demands, thereby protecting your non-structural components. And I think you can go to the next slide, Larry. And so based on that criteria, we wanted to select a ground motion that would able to show us these large higher mode effects. We wanted the ground motion to have characteristics in the higher modes so we could see those higher mode accelerations. And then we wanted to choose a ground motion that would also be comparable, say at the first mode and looking at the displacements. And so we looked at something like 80 plus ground motions. Jim showed one of them that was used for the Lehigh testing. And we ended up at two ground motion sets. One is the Northridge ground motion, and the other one was JMA Kobe. And we chose those at 40% and 100% of that ground motion. That last test is to be determined because we're doing 5 tests leading up to that point. And if you show the next slide, Larry. And so this is just a response spectrum of those 2 ground motions. So the dotted red is the Northridge ground motion, and our second mode period's around 0.25 seconds. And so that's sort of off to the left. And in that higher mode period range, the Northridge has higher acceleration content at that second mode. In contrast, the JMA Kobe, which is the second ground motion that we selected, has a higher acceleration content at that first mode period, around 1 second. So now we can sort of see how these acceleration effects are affecting the MRF with spine with FLC system. And then I think you can go to the next slide. And so again, we're running a suite of ground motions and it's consecutive. And so choosing how those ground motions, where we start and whether we reverse the ground motions to sort of negate the effects of residual drift were really important. And so this is where Brian was spending, I would say, mainly a sleepless night running a set of these anywhere from 4 to 6 ground motions, and then looking at the deformation demands and how that led to the next test. And so far, the results from our numerical model, even given the epistemic uncertainty, have been pretty good. So just real applause to the students who worked on these numerical models for this project. And Larry, I think this is my last slide, so I'll hand it back over to you.
All right, thanks, Barb. Moving on to talk a bit more about the experiment itself. What you see here probably looks a bit familiar because a big part of the building that we're testing was part of the Tokyo Metropolitan project. What we did was to take the base isolated portion of their test building and use it again because it was essentially undamaged after their testing program because of the isolation. And because of the dynamic properties that we needed for our test, we needed to make the building taller. And so you can see here in blue, we added a story onto the 3-story, what was the 3-story base isolated structure. And we also added the spines on the exterior connected to the main building with these force limiting connections. So here you see a photo of the Tokyo Metropolitan project that Masahiro described a few minutes ago. You see on the right the base isolated portion of the building that we are using as our test building. One of the interesting logistical challenges of this project was fabricating the new top story here in the United States, along with the spine and the FLC components, and then shipping them to Japan, having them all constructed in Japan and put together and fitting on top of the existing building that was built in Japan. And so this is another great opportunity just to thank our Japanese colleagues who have worked tirelessly, especially in the last few weeks, the last couple months, to make all this happen as we were, the US side of the team was here in the US. So we've become good friends with WhatsApp, international research collaboration through WhatsApp. So here you see a little screenshot of one of our very long and ongoing thread that we have. So we've been here in the US sitting up at night with our phones and computers, listening for the ding of WhatsApp and what the latest question or challenge will be that we need to help resolve. But Masahiro and Taichiro have been fantastic collaborators. They have a big team of students and postdocs and technicians. Yusuke, a lead person at EDefense. I can't say enough about their efforts and their enthusiasm for this project that has really made it happen. So here on the right, you see the full 4-story building with spines intact, scaffolding there for construction and observation. And so I just want to show you one video. This is the second test that we conducted earlier in the week, the 100% Northridge. So we conducted a 40% Northridge. You'll see here that from that 40%, there was some partial toppling of some of the hospital contents. And so you'll see what happens to that as the 100% motion continues. So let me just play this. And what you'll see here is the spine does its job of enforcing more or less uniform story drifts over the height of the frame. But because we have rigid connections and we do not have the FLCs active in this portion of the test, you'll see we still get significant accelerations that lead to those problems for the hospital components. After we did this test, we then released the rigid attachment such that the FLCs were active at the first and third elevated levels. We reran the 40% Northridge, and we did reset the hospital components, and so we did not see any damage or toppling of them in the 40% Northridge that we ran as our third test earlier in the week. So very soon, we will all get to see what happens with the 100% Northridge MRF plus spine with the FLCs active. So that's coming up very soon. With that, I want to thank you very much for your attention, and thank you all for joining the meeting. And also, again, just say a huge thank you to all of the collaborators on this project, and especially our Japanese colleagues who have just been fantastic. And we owe them a great debt of gratitude because of all their work to make this project happen in a very unusual year for all of us. Thank you.
Thank you, Larry, and Barb, and Jim, and Richard, and of course, the collaborators from Japan led by Professor Kurata. This is amazing. I was just watching, and it's hard when you go there and spend weeks and months and doing it the way you guys did it. This is amazing, and it's a testament of the strength of this collaboration. Great job, everyone. We are about 4 minutes past 11 on the agenda, so we had allocated a very small time for questions. Would you guys entertain one question if there is one from the audience? I don't know if they can unmute or ask to unmute, and I can see if I can do that. By the way, now
sure, that would be fine. We soon need to make our way virtually to the lab to help with test preparation, but I think we could take a question or two if there's time for it.
If not, we can do it at the closing session if you guys are going to hang around.
Julio, I just shared the YouTube link for the streaming.
Perfect.
In chat, so please let everyone know. Yep. I'm just moved to the control room EDefense, so you can see how EDefense set up now, ready for the test, and a lot of the cameras. You can see the connections.
Thank you, Masahiro.
Thank you. Thank you very much. And you heard
students working for the data analysis. Yep. Bye-bye.
Fantastic. Thank you, Masahiro. And thank you, Larry. I think then in the interest of time, because I know that when they're ready and you guys need to go, we'll move on to the next session. Thank you, everyone. And if there are any questions, we'll catch them at the end then.
All right. Excellent. Thanks.